Thanks for the introduction, Nigel. It's really nice to be here. Thanks for coming, everyone. I'm going to tell you about this stuff, which is pseudorandom correlation generators and their applications to multi-party computation. So the things I'm going to talk about are based on some joint works with lots of people: Alette, Geoffroy, Nive, Yuval, Lisa, and Peter. And the rough outline for today is I'll introduce this concept of pseudorandom correlation generators, or PCGs, and some motivation to using them for multi-party computation in the preprocessing model. And then I'll give a bit of background on the learning parity with noise, or LPN assumption, which I'll be using for some constructions, and explain some of the difference between this and LWE, which I guess most of you will be more familiar with. And then I'll present two main constructions. So firstly, a PCG for generating oblivious transfers from LPN, which leads to this two-round silent OT extension protocol we have, which is upcoming at CCS. And then the second one is a more theoretical construction for generating more general linear correlations over finite fields, also from LPN. And then lastly, I'll present some kind of ongoing work we have on making this concretely efficient under some new variant of ring-LPN. Okay, so the motivation here is secure computation in the preprocessing model. So here we have two parties, and in the middle we have this trusted dealer who generates some correlated randomness and distributes it to the parties. So throughout this talk, whenever I have this kind of situation with the trusted dealer, I'll always have the dealer in the middle, and then the parties on the left and the right when they're actually like doing the protocol and interacting or whatever. Okay, so then the idea of this is that this correlated randomness can be used to help the parties perform two-party computation in the online phase where they take their inputs x and y and evaluate some function on both of the inputs. And the nice thing about this is that the online phase is then very efficient. It can be almost entirely information theoretic. The computational and communication overhead compared with the size of the function you're computing can just be a small constant factor over computing the function in the clear. But the main downside of this is if you don't have some trusted dealer available to generate the correlated randomness, then you have to do an interactive protocol to generate these random values, and this tends to be very expensive and ends up dominating the total cost in terms of both communication and computation for the actual 2PC protocol. So the goal of what we want to construct today is secure computation with a silent preprocessing phase. So where instead of having a setup functionality or trusted dealer, which gives us a lot of correlated randomness, we just distribute some very short correlated seeds, which can then be completely locally expanded to produce as much pseudorandomness as we want to use for the MPC protocol. And of course, the nice thing about this is that when we actually replace the trusted dealer with some protocol, hopefully this protocol we use to generate the seeds can be much simpler and much more efficient, much less communication than generating the entire correlated randomness as before. Okay, so the tool we'll use to construct MPC with silent preprocessing is this object called a pseudorandom correlation generator, which is kind of a distributed analog of a PRG for generating correlated randomness. So we have some correlation, which is some distribution that outputs pairs of values R0 and R1. For example, this could be random oblivious transfers, or it could be multiplication triples used for MPC. And we have two algorithms, a seed generation algorithm, which outputs two independent seeds for this correlation, and then an expansion algorithm, which is locally applied to just one of the seeds to output some sample from the distribution. Now, the ideal security guarantee we want from a pseudorandom correlation generator would, of course, just be that these R0 and R1 values that come from expand are, in some sense, identically distributed to a sample from the correlation. Unfortunately, that's not really possible to realize in practice, just because a basic kind of information theoretic argument and the fact that we have compressed seeds, which are much smaller than the output of the correlation. So the actual security definition we require just says that if we look at just one of the seeds and then look at the output of the correlation from the other seed, then the joint distribution of these things looks the same as if we took the other one sampled from a real correlation. So if we take R1 from the distribution, conditioned on this, the other correlation being equal to what comes from the expansion function, then we get something that is computationally indistinguishable. And this definition may be a little unnatural, but it turns out this suffices in most applications of multi-party computation to replace a correlated randomness which comes from some ideal trusted dealer. Okay, so I'll just give a quick overview of some constructions of PCGs that have appeared over the last years. So these were kind of implicitly considered going back to the late 90s and 2000s. And this works related to pseudorandom secret sharing, which produce simple and pseudorandom linear correlations for additive or Shamir secret sharing schemes. But then going beyond linear correlations took quite a long time, and it wasn't until last year when we had the first concretely efficient construction for something called a vector OLE correlation, which is kind of a scalar-vector product on random values that's then secret shared. It's based on the LPN assumption. And then the works I'm going to talk about today come from two papers, one at Crypto this year, and then another one coming at CCS, where we build upon this vector OLE work and then look at PCGs for a variety of other correlations like OT, low-degree polynomials, and other things. And the ones I'm going to focus on in the talk today are the OT correlations and these constant degree correlations from LPN. Okay, so now let's go to some background on the learning parity with noise assumption and its comparison with LWE. So let's play a little game. So which assumption is this? Depends on P. Very good. Bit of a trick question. So yeah, traditionally, if you look at LWE, then this is always some P greater than 2. And then LPN, we restrict to the case P equal to 2, learning parity, kind of binary. Well, both of these assumptions are just essentially solving this linear system, A times S, when you have some kind of quantity of noise added to the outputs. But in this talk, I'm actually going to be thinking of an arithmetic generalization of LPN where we can allow any modulus P even greater than 2. So this is sometimes also called a random linear code assumption, or I think it's also known under different names. I just think of it as LPN. So now you might be wondering what's the difference between these two things. Well, they both have a uniformly random secret chosen from Zn. The only difference really, when you look at these arithmetic versions, is the noise distribution of this vector E. So LWE, we always have that each coefficient of E is going to be somehow bounded in size, or maybe from a Gaussian distribution. Whereas in LPN, the smallness actually comes from the Hamming weight. So when we have this arithmetic generalization, then each coordinate of E is either going to be 0 or it's going to be uniformly random mod P with some probability. And in this case, instead of looking at the kind of Bernoulli-like distribution on each coordinate having independent noise, I always think about just fixing some Hamming weight of the error vector and then sampling a random E with this fixed Hamming weight. These are kind of the same assumptions if you're careful with the parameters. Okay, so these two assumptions, they look very similar, but actually the things you can do with them turn out to be very different when you look at cryptographic constructions. So LPN, we know we can get all of these symmetric type primitives like pseudorandom generators, secret key encryption, digital signatures, and all of minicrypt. And if you allow a slightly stronger assumption where you have a very small noise distribution, then you can also get cryptomania, so you can get public key encryption, oblivious transfer, and hence multi-party computation from LPN. And of course, all of these things we can also get from LWE, and actually a whole lot more. So with LWE, we know we can get additively homomorphic encryption. We can get fully homomorphic encryption, advanced things like functional encryption, and use these to build very succinct forms of multi-party computation. And these things we don't know how to build from LPN. Even additively homomorphic encryption if you require a kind of strong pseudo-randomness requirement on the kind of added summed up ciphertext, then we don't know how to do that from LPN. But in this talk, what I'm going to show is that there are some things in this area which you can get from LPN using different techniques. So what I'll show is that there's a very simple MPC-friendly PRG, which we can get from LPN. This has just been a standard symmetric primitive, but it turns out to be very useful for constructing succinct forms of multi-party computation. So kind of optimal communication, MPC, for special classes of low-degree functions. OK, so just to give you a flavor of what's to come, I'll just quickly show you what these pseudo-random generators from LPN look like. So the most basic construction simply takes a secret S and a noise vector E, where these are seen as a seed for a PRG. So imagine that they're kind of compressed into the smallest uniform string that they could be. And then the error vector E is expanded to the sparse vector. We compute AS plus E. So that's then a deterministic pseudo-random generator. And then there's another construction, which I call the dual construction, which is somehow equivalent but looks a little different, where we only take a sparse error vector. And instead of computing AS plus E, we just multiply this error by a compressing matrix H. So here the secret has kind of disappeared. And again, we've got, say, another random-looking matrix H, which is public, multiplied by the error vector. So these two things are equivalent, which can be seen by taking H to be the parity check matrix of the code, which is generated by the matrix A. And so if you take this and multiply on the left by H, then this goes out to 0 because it becomes a code word, and you get H times by E. So these are kind of equivalent constructions, but they have different properties. So what we're going to be interested in is getting as high a stretch PRG as we can. So maximizing the expansion factor, which is the number of rows M of this matrix here, and the parity check matrix X and has M minus N rows, where N is the dimension of S. So if we want to increase M, then for security, we typically have to either increase the dimension of the secret or increase the error rate of the error vector. But when you do this in the primal construction, either of these two things will always increase the entropy in the seed as well, so you kind of limit this stretch. It turns out you can't get beyond quadratic stretch from this construction. So a seed of n bits going to n squared bits output. Whereas if you do this with the dual construction, we can increase m and then just increase n whilst keeping the Hamming weight of the error vector fixed. And because we have the secret kind of disappeared in this construction, so increasing n doesn't actually change the size of the seed from the PRG. So the really nice thing about this dual construction is we can get an arbitrary polynomial stretch for this PRG if we assume LPN is still secure when we have this fixed Hamming weight of the errors. And if you look at the best known attacks in this situation, they're essentially exponential in the number of errors in the error vector. So this seems like a solid assumption to make. Now, of course, one downside, which you might have noticed here, is that if we're increasing m and n to be really, really big, then this actually becomes computationally very expensive because we have to do this huge matrix multiplication just to compute the output of the PRG. So in practice, when we do this, we'll actually look at some kind of structured variants of LPN, where we have some special structure on the matrices H and A, so that we can compute this more efficiently, say in linear time or quasi-linear time. OK, so any questions on LPN or anything so far? Feel free to interrupt if you have anything. So now, before getting to the main constructions, I'm going to just show you this high-level blueprint, which is how we exploit this sparsity of this LPN pseudo-random generator in multi-party computation. And the main idea is that we want to take one of these LPN error vectors and then compress it into some secret shares, which individually are much smaller than the length of the error vector. And we'll use different tools for doing that in the two different approaches I talk about. And then these compressed shares should be able to be locally expanded to produce some additive shares of the secret so that we add together and get the original sparse vector. And then the second step, which is the main key ingredient in both of the constructions, is to have some secure two-party protocol for generating these seeds corresponding to some, say, random sparse error vector in MPC. So this is the kind of MPC-friendly nature of this error distribution, these PRGs, that we'll exploit by having specific methods for doing this for the different applications. Okay, so the first construction, I'll be looking at let's look at a PCG for generating oblivious transfers from LPN. I guess everyone knows OT. We have two parties, a receiver and a sender. The receiver wants to learn XB without learning anything about X1 minus B, where the sender inputs X0 and X1. Of course, the downside of OT is that it's kind of expensive. We know we need public key cryptography to do OT. But to get around that, we have OT extension, which is this technique for taking, say, a small number of seed oblivious transfers and then extending them to create many more oblivious transfers using only symmetric key cryptography. So we only have to use public key cryptography for the first few initial OTs. The downside of most OT extension techniques is that this extension phase comes with some quite high communication costs, with this security parameter overhead for each oblivious transfer we want to create from OT extension. So using the PCG, we'll try to avoid this and get something we call a silent OT extension, where the total communication for n random OTs is going to be sublinear in the number of OTs. Okay, so going towards this, the kind of rough structure of the construction will be to first build something called correlated OT. So this is where the sender's messages on the right here are always correlated of this form, say WI and WI plus Y for some fixed string Y. So in the receiver's output VI for choice bit BI can always be written as WI plus BI times by Y. So this is a more restricted kind of OT. But going back to this IKNP construction for OT extension, we can just apply a hash function to the outputs of the OT and convert these to random OTs. And then once you have random OT, it's very straightforward to de-randomize these into OTs on chosen messages with some amount of communication. Okay, so the main goal is then to construct a PCG just for this correlated OT. So this is going to be some kind of compressed version of these correlated OTs, where the receiver has a long vector of bits and another long vector of strings. The sender has another vector of strings, which when added together give the vector of bits or multiplied by some fixed value y, which is the correlation which the sender had for the correlated OT. So this is kind of a vector scalar product of a specific form, where this vector of b is always bits, whereas this y has to be some string, or you could think of it as a binary extension field element of, say, 128 bits long. Okay, so the construction we have follows this blueprint, where we have a setup phase, which produces some random-looking seeds to each of the two parties, and then this expansion to produce shares of some kind of sparse vector will be done using a puncturable pseudorandom function. And this produces shares of not just a sparse vector, but a sparse vector multiplied by this value y, which is the OT correlation known to the sender. And then once I have these, we can use the kind of simple dual construction of the PRG from LPN by just multiplying these by this, say, the random matrix H, and then we end up turning this into something where the sparse vector becomes a pseudorandom vector. And because we're just multiplying by a public matrix, this is all linear, so it can be applied locally to the shares without any interaction. That gets us the correlated OTs, which are then hashed to get random OTs. Okay, so I said we need a puncturable PRF. This is like a variant of a pseudorandom function where we have two different ways of generating keys. So we have this kind of standard master key generation, which allows evaluating the PRF at all of the points in the domain as usual. and then a special punctured key, which can evaluate at every point except for some special punctured point, alpha. And the security is a given some punctured key for a point alpha, the PRF evaluated at alpha is pseudorandom. So it completely hides that specific evaluation. So there are some very simple constructions of puncturable PRFs based on the classic GGM construction of a PRF from any length doubling PRG, where the size of the master key is just lambda bits, and the size of a punctured key is scaled by this log n factor, where n is the domain size of the PRF. Okay, so we'll use a punctured PRF to do this compression of sparse vectors. So we have some trusted setup for now, which will generate a punctured PRF key and puncture it at a random point alpha. So then each of the parties gets either the punctured key and the point alpha or the master key, and then just computes all of the evaluations of the PRF at every point in the domain. So this is some polynomial-sized domain of n points to produce a vector of length n, where here the receiver who can't produce this value at alpha, where it's punctured, will just define this to be 0. And if you look at XORing these two things together, then because these are the same everywhere except the punctured point alpha, we end up with this secret sharing with a sparse vector, where taking out the point here, which is the PRF evaluated alpha, we get the random value multiplied by this sparse unit vector. So here we have this kind of asymmetric setting where the product outside of the vector is known to the sender, whereas the point, which defines this unit vector, the alpha, is known to the receiver. And this gives us this compressed form of this sharing of a sparse vector. We've compressed the shares from, say, n bits, or lambda times by n bits, if this is lambda bits long, down to just lambda times by log n bits, which is the key size for the punctured PRF. Okay, so go towards using this to compress. So one small tweak we can make to this is to multiply by some arbitrary value y, which is given to the sender in the preprocessing, by also giving the receiver some the PRF value at the punctured point masked by y. They can use this to change this blue dot to some chosen value y instead of just being random. Okay, so that gives us a sharing of a unit vector. If we want a sparse vector for LPN, then the simplest approach is just to take, say, t of these, add them up, and get a vector of weight t, where we have to use the same random value here in each of the unit vector constructions. Now this has some kind of factor t overhead when you compute the expansion of these, because you have to compute each one separately and add them up. There is a way around that. There's actually a very recent paper just on ePrint a few weeks ago where they show a cuckoo hashing technique for kind of optimizing this and evaluating the sum of all of these punctured PRFs in linear time. An alternative, which we use in our work, is to instead have this kind of regular structure on the error vector so that you can write it as a concatenation of several weight 1 vectors. So that then you just need to evaluate something which has total length n, and again gives you linear complexity. So this involves relying on a slightly stronger version of the LPN assumption, which you can avoid with this cuckoo hashing technique. Okay, so combining these two things together, we have this mechanism of generating, with a trusted dealer, these sparse times by pseudo-random products, where one party has the pseudo-random value y, another party has this sparse vector. And this pretty much gives us everything we need for the silent OT extension by just multiplying by the random matrix, so that we see, after we've multiplied the shares and compressed them down to something, then this multiplies the error vector by h, so we get y times by something pseudo-random under the LPN assumption. And this gives us correlated OTs, which we can then hash to get random OTs. Okay, so that's the OT extension protocol with the setup phase for distributing some punctured PRF seeds. Now I'll quickly give you a little glimpse of how to generate these seeds in a distributed way, which gives us the entire protocol for doing
When you actually, so when you want to produce one of these correlated OTs from your setup,
Yeah.
you just apply different logs into the punctured PRF, yeah?
So whenever you're evaluating the punctured PRF, you always evaluate it at every single value in the domain. Yeah, so you're just...
So I've got this, so the whole point of OT extension is I do a bunch of I do some stuff at the beginning,
Yeah.
and then I can keep getting OTs.
Yeah.
So what is this thing that allows me to keep getting stuff?
So you can keep getting, but you have a bounded number. So the number of OTs you get is proportional to the domain size of the punctured PRF. Yeah? Yeah? Yeah, so this sparse vector, which you expand by, for each entry of the vector, you get from one PRF evaluation. So domain size n, you get a vector of length n. And then you compress it slightly when you multiply by the matrix. But for the setup phase, we always need that this domain size has to be polynomially bounded. So we can't get a kind of arbitrary expansion.
Kind of do for the original OT extension.
Yeah, well, you have to interact for each one. And so for this, you can always interact again and then create more seeds and do it as many times as you like. Okay, so we have a puncturable PRF. Or we want to build a puncturable PRF and also create this distributed setup procedure where one party bets the master key and another party gets this punctured key at a point alpha. Here, this is the kind of standard tree-based construction of a puncturable PRF from any length doubling PRG, where at the root of the tree we have the master key k, and then at each node of the tree we expand the current key with the PRG to produce two new seeds, which are then used as seeds for the next level going down. And then the final leaf nodes at the tree will define the final, all of the outputs of the PRF. Okay, so then the punctured key for some point alpha is going to be obtained by taking every node on the tree which is adjacent to the path alpha. So these yellow nodes marked here will be then given to the receiver. And the receiver can expand these using the PRG and look that they can then obtain at the base of the tree every single point except for this punctured point at alpha, because it doesn't have the required nodes to be able to compute this path. So that's the punctured PRF. Now we want to distribute this in some way in MPC. And the way we'll do this is based on this Durner and Chalat protocol, which does a similar thing for a distributed point function. We adapt to a puncturable PRF here using Oblivious Transfer. So suppose that we've kind of got partway through the tree, and the receiver has these tree values for, say, the first two levels of the tree. It can compute everything underneath them. They're not the ones on here. So for the next level, the receiver then wants to learn this missing value to help it compute the ones below, whilst not learning anything about the one that kind of defines the path to alpha. So we'll transfer this next level to the receiver using OT in the following way. So the receiver either wants to take the left child or the right child of this node which it knows here. The problem is the sender doesn't know exactly which of these pairs of leaves the receiver is using, right? It could be any of them across here because the sender doesn't know the point. The receiver will just input left or right into the OT as a choice bit, and then the sender can compute the sum of all of the left-hand nodes on its tree here, and then the sum of all the right-hand nodes on its tree. And because the receiver actually knows all of the rest of the nodes of the tree, except for these two here it's interested in, then it can use all of the rest of the tree to kind of unmask the remaining ones and recover exactly the right value to define the punctured PRF key. And then you can kind of iteratively apply this to generate the entire punctured PRF key using log n OTs. And the really nice thing about doing this for a punctured PRF is that all of these OTs can actually be performed completely in parallel, because if you look at the inputs for these, they're actually independent and can be computed in advance. So this means to do the setup phase for a punctured PRF, we just need log n OTs all in parallel, which can be done in 2 rounds of communication from any 2-round OT protocol. And this is all we need to do for the setup. So when we do this for OT extension, this actually implies a 2-round OT extension for the entire kind of silent OT phase. And you can also use this to do 2-round OT on chosen inputs instead of random inputs by kind of doing this conversion from random to chosen OT in parallel with the setup phase. So this also gives the first concretely efficient 2-round OT extension protocol. So all of the efficient protocols before, based on IKNP, require 3 rounds. The only known way to do this before this work was Beaver's non-black box approach based on garbled circuits, which is very expensive. OK, so some kind of other extra things we have in the paper is a method to do the setup procedure with active security. So the previous method for setting up punctured PRF keys allows some kind of cheating by the sender if it doesn't input the correct values into the OT. We get around this using some lightweight consistency checks to kind of enforce semi-honest behavior. This does allow some kind of selective failure attacks, which actually allows the sender to maybe try to guess a few bits of the LPN error vector, which we can't really work around efficiently. So we generally have to kind of add this extra assumption that LPN is still hard with maybe on average 1 bit of leakage on the error vector. But otherwise, these checks are very simple and efficient. And then we have an implementation of the protocol, where, as I said before, the main challenge in doing this is going to be this matrix multiplication by this huge parity check matrix H, which, say, if we want to produce 1 million OTs, then this is going to be 1 million by 500,000 or 2 million matrix multiplication. So to optimize this, we use a quasi-cyclic code where matrix multiplication corresponds to polynomial multiplication. This is just binary polynomial multiplication over F2. And then this gives us security not related to standard LPN, but now based on this quasi-cyclic syndrome decoding problem or some variant of ring-LPN, which is essentially the same assumption used by several recent post-quantum crypto systems, which are ongoing candidates for the NIST competition. OK, so now for a quick comparison of our implementation with the standard IKNP protocol, which is the previous state-of-the-art OT extension. So first off, you just look at the communication cost for producing 10 million OTs. And with the silent method, we have, say, only 100 kilobytes or so, and this goes up to more than 100 megabytes for generating them with IKNP, purely because you have to interact for every single OT. We just have this very cheap setup phase. The price we pay for this, of course, is we have so roughly a factor of 10 difference in computation, which you see in the LAN setting here. But so if you're in some setting where you can run in a local network and you don't pay anything for communication, you probably still want to use IKNP. But as soon as you have to pay some kind of price on bandwidth, or you're moving to some slow network like a WAN, then quickly these costs, this becomes much more worthwhile. So already in the 100 megabit WAN setting, we get a 5 times performance improvement of IKNP. And then moving down to very slow networks, this goes up to around 50 times. OK, so yeah, that's the silent OT part. Any questions on this before moving to the second part? Dragos?
In the paper, you had the numbers for 1 and 4 threads.
Yeah.
Because each thread occupies a lot of memory, or you just didn't want to go with more threads?
Yeah, I think that's just all we tested. Yeah, you could do more. Maybe it's just the machine didn't have so many threads. I'm not sure. I don't think it needs a huge amount of memory beyond standard OT extension. OK, so that was this PCG for OT, which is very good has very good concrete efficiency. Gives you OT, which can be used in a lot of applications for MPC, but typically most useful for MPC for binary circuits. But if we want to do more arithmetic computations, like operations over the integers, then we want more than OT. We want, say, something called OLE, which is oblivious linear function evaluation. this arithmetic generalization of OT, where a receiver inputs an element of ZPX, and then we'll receive this linear combination, AX plus B, defined by the send of two values A and B. So this is also related to multiplication triples, which are used for MPC. If you have two OLEs on random values, then you can locally compute a two-party multiplication triple. Okay. So in this construction, I'm going to not use a puncturable PRF. Instead, we need a slightly stronger tool, which is something called a distributed point function. So this is kind of an, you can think of this as a variant of a punctured PRF, where no party knows the punctured point alpha. So we have some point function defined by alpha and a point beta, which map to 0 for every x not equal to alpha, and is equal to this special value beta at the point alpha. So distributed point function gives us a way of secret sharing this function, where we have a generation algorithm which takes the points alpha, beta, and outputs two keys, S0, S1, and then some evaluation algorithm which each party can locally apply to their seed, and the same public input x, such that the XOR of these evaluations is going to be the point function applied to x. So you can imagine, similarly to the punctual PRF, now both parties can take one of their seeds and then evaluate the distributed point function at every point in the domain from 1 up to n, and this will produce these long vectors y0 and y1, which are now a secret sharing of this unit vector, or this weight 1 vector, with beta at exactly the point alpha and 0 elsewhere. Okay, so the only difference with this and the punctural PRF is that now nobody knows the point alpha, so this is totally distributed. And constructions of distributed point functions are a little more complex, but asymptotically at least end up having the same key size as the punctual PRF and are based on this GGM-like construction in some way. So it's still very efficient concretely. Okay, so now we want to generate compressed forms of correlated degree 2 functionalities, say. So instead of just going for OLE, let's say we have a totally general degree 2 function, so we want to compute a tensor product of two random shared vectors. Okay, so we'll take two sparse vectors, a random vector E and random vector F, both of Hamming weight T, and then look at the tensor product of these. So this is going to be a sparse matrix. So if these are weight T, then this matrix will have T squared non-zero coordinates. And this means we can take every entry of this matrix and represent it using a point function of size n squared, compute T squared of these distributed point functions, and distribute these to the two parties. So this gives us a kind of way of secret sharing the compressed tensor product of these two error vectors. So spelling this out in a little more detail, we have this trusted setup algorithm which will sample two random vectors and then create distributed point functions for the tensor product of these to give the seeds to the two parties. And now they will evaluate each of these DPFs at the entire domain. So this time the domain is size n squared, and XOR these together so they produce this random shares of this matrix, where when they add up the two matrices, they get the tensor product of the sparse vectors E and F. And now, going from here, it's very simple just to randomize these sharings by multiplying with the big matrix H using the LPN-based PRG. So we can first multiply on the left by matrix H, and then multiply on the right by H transpose to randomize both the E component and also the F component, which gives an additive secret sharing of the tensor product of these uniform vectors HE and HF. So you can use this to produce a pseudorandom correlation generator for any degree 2 function. Since once you have tensor product, you have all the degree 2 monomials. The downside of this approach is that computationally it's very expensive. Because now we always have to do these kind of full evaluations of distributed point functions of domain size n squared. So we need at least n squared computation. That's not even counting the matrix multiplications we have to do. So it's not really something practical Because if we want to produce n OLEs with little o of n communication, then ideally n is going to be really, really big, right? But we don't want to pay this n squared cost. But I think theoretically this is quite an interesting result. You can also extend it to arbitrary degree d correlations for any constant d in a very natural way. And this actually implies a homomorphic secret sharing scheme for constant degree polynomials from only the LPN assumption. We have this exponential in d computational complexity. So it's not something practical, but it's something we didn't know how to do before from LPN. And this kind of constant degree homomorphism we could only previously get based on things like LWE or DDH. OK, so the ideal thing we'd have is some concretely efficient version of this degree 2 construction where we can just pay, say, a linear and n amount of computation to get an n oblivious linear evaluations, or n OLEs. So the idea to do this is kind of similar to fully homomorphic encryption schemes based on ring-LWE. So kind of analogous to the BV construction where you replace tensor products after ciphertext multiplication of two LWE ciphertext with a multiplication of two polynomials so that you don't get this quadratic blow-up after multiplying. So in our case, it's very simple. We just have two error vectors, which this time will represent as sparse polynomials, and then compute this sparse polynomial product of these error polynomials, say modulo x to the n plus 1, if n is a pair of 2. And this is a polynomial now. It's only of degree n. So we haven't blown up the size to n squared. And we still have something sparse. It has around t squared non-zero coefficients. So we can share this using a distributed point function. And when we do this to generate multiplications for OLE, what we'll end up sharing is shares of this product where we have 4 sparse polynomials, so E and E prime, which will be randomized to produce one set of kind of polynomial products, and then F and F prime will be randomized separately to produce another one under some variant of the ring-LPN assumption. So to distribute this to get a PCG, we just need to take all the cross terms of the error polynomials here. And remember, H is this public random polynomial instead of the public matrix H. So we can do this using DPFs. But what this gets us is then some secret shared product over the polynomial ring. So we have polynomials mod p and x, mod some x to the n plus 1. This gives us a single kind of very large OLE in this polynomial ring. Of course, if we have the right kind of ring, which splits completely into linear factors, then this is equivalent also to a large batch of n OLEs just in ZP. And we have t squared DPFs to share these cross terms of the sparse polynomials. But as long as n is large enough, which ideally we want it to be, then the computational cost is going to be dominated by just polynomial multiplications, which is n log n, instead of n squared as before. But what about security? So now instead of just relying on some kind of general LPN problem, we really want to have this variant of ring-LPN over some ring which fully splits into linear factors modulo p. So this is kind of the same as the assumptions people use for ring-LWE, but for LPN it hasn't really been looked at, especially in this arithmetic setting with some large prime p. So we know that if p equals 2, then there are actually some attacks on this, and this is considered a kind of bad instantiation of ring-LPN, and you can break it with a special structure. But as soon as you extend this to some much larger p, these attacks don't seem to apply. And although as far as I know it hasn't really been studied much, it seems like it could be secure. And I hope that people will study it more and we can get some more confidence in this. OK, so that's everything I wanted to say. So to conclude a little, the first part was on this pseudo-random correlation generator for random oblivious transfers, which got this very practical construction with almost zero communication to create a batch of random OTs and 2-round NT extension. And then we looked at generalizing this to arithmetic setting to do oblivious linear evaluations over finite fields. where we can do things from LPN, but it's very computationally expensive. And if we rely on this fully splitting variant of ring-LPN, then we can actually get something that's concretely efficient. So there's many open problems in this line of work. So on the OT side, I think there are still some optimizations we could try to do for the implementation. Like perhaps we can have some better choice of parity check matrices instead of quasi-cyclic codes, which may be ideally something which is linear complexity instead of quasi-linear. So as I said, there's this cuckoo hashing optimization for puncturable PRFs, which we could also apply to implementation. And for the active security case, it would be nice if we can also make cuckoo hashing work, because this paper only looked at semi-honest security. And then for this OLE case, of course, I think the most important question is to further study this arithmetic ring-LPN assumption, which we've been looking at. So far, we haven't really managed to break much, as long as you're careful. Another kind of interesting possibility is that as a fallback, you can rely on slightly more conservative assumptions, maybe not with a fully splitting modulus, where you have to pay some additional communication to generate the OLEs, but it's still something quite small. And then more broadly speaking, going beyond simple degree 2 correlations, it'd be nice to have pseudorandom correlation generators for more things, like, for example, generating random secret shared truth tables, which are often used for MPC, generating random shared bits, modulo prime, generating garbled circuits. If we have a way of compressing garbled circuits that's efficient, that would be something really amazing. Probably very hard, but it's good to think big. And that's everything. I have to take questions.